For this problem, we are given a solid whose base on the xy plane is the region bounded by the parabola y equals x squared and the line y equals 2. When sliced by planes perpendicular to the xy plane and the y-axis, the cross-sections of the solid are equilateral triangles. Our task is to determine the volume of the solid. Let's examine the base of the solid on the xy plane. One bounding curve of the base is the parabola y equals x squared. The second bounding curve is the line y equals 2. The base of the solid is the region enclosed by the two curves. Since the region is symmetric with respect to the y-axis, each cross-section perpendicular to both the xy plane and the y-axis has its base bisected by the y-axis with both its endpoints on the parabola. Let's look at the base of the solid from a different vantage point, slightly to the side and above the xy plane. Projecting vertically above the xy plane are the equilateral cross-sections of the solid. We give each equilateral triangle cross-section a thickness along the y direction so that we get a parallel slice or parallel section of the solid. The solid is made up of many of these parallel sections. And so this is the solid whose volume we are to find. We find the volume of one section, add up the volumes of all the sections to create a Riemann sum for the volume of the solid, then let the maximum thickness of all the slices tend to 0 to get a definite integral for the volume of the solid. To find the volume of one section, we assume that the green shaded side of the section is perpendicular to the equilateral triangle cross-sections. This implies two things. First, we are assuming that the vertical cross-sections of the section are all congruent to the front and back equilateral triangles. Second, the volume we obtain will be an approximation of the exact volume of the section. Because of our assumption, the approximate volume of the section will be equal to the area of the equilateral triangular face multiplied by the thickness of the section. Suppose that we have n sections in all, and the section shown on screen is the ith section. We denote the area of the triangular face of this section by a sub I. The thickness should be perpendicular to this face and parallel to the y-axis. As such, we denote the thickness by delta sub I y. Let V sub I be the volume of the ith section. Then V sub I is approximately equal to the cross-sectional area A sub I times the thickness delta sub I y. Since the thickness reflects the change in the y-coordinate from the front triangular face to the back face, we must express A sub I in terms of y. Let the y value along the base of the front equilateral triangular face be y sub I. Then we must find a formula of A sub I in terms of y sub I. We don't have one. At the moment, we denote this formula by A of y sub I. And V sub I will be approximately equal to A of y sub I times delta sub I y. A of y sub I being the area of a triangle is equal to half times the base of the triangle times its height, h. The endpoints of the base of the triangles are symmetric with respect to the y-axis. And since these endpoints lie on the parabola y equals x squared with y equals y sub I, one endpoint has x equal to the square root of y sub I. The other endpoint has x equal to minus the square root of y sub I. Therefore, the base has length equal to the square root of y sub I minus the square root of y sub I, or the base is 2 times the square root of y sub I. We apply a little trigonometry to find h in terms of y sub I. H, of course, is perpendicular to the base. In addition, because the triangular face is equilateral, its base angles are both equal to 60 degrees in measure. 1/2 of the base is the square root of y sub I. Using the fact that tangent 60 degrees is the square root of 3, h must be equal to the square root of 3 times the square root of y sub I, or the square root of 3 times y sub I. We simplify a of y sub I by cancelling out 1/2 and 2. The square root of y sub I times the square root of y sub I is y sub I. And so a of y sub I is equal to y sub I times the square root of 3. Therefore, v sub I is approximately equal to y sub I times the square root of 3 times delta sub I y. Now, v sub I is the approximation for just the ith section. And remember that there are n parallel sections. Therefore, adding the v sub i's, the volume of the solid is approximately equal to the sum from I equals 1 to n of y sub I times the square root of 3 times delta sub I y. This is a Riemann sum for the volume of the solid. Let the maximum thickness of all the parallel plane sections tend to 0, so that the Riemann sum tends to a definite integral. The volume of the solid should be equal to the integral from 0 to 2 of y times the square root of 3. The viewer can check as an easy integration exercise that the value of this integral is equal to 2 times the square root of 3 cubic units.